Thanks for the introduction. So this is something that I've worked on for probably for at least 2.5 years, maybe even more than 2.5 years. So I still remember that like in 2022 Eurostat, I think I spent, like before that I spent probably. Louder, please. Okay. The mic is not working, or okay. Okay, I'm not loud enough. Okay, that's yeah. So this is a project that I spent probably 2.5 years at least to work on. Yeah, I think I remember there's a few deadlines. Before the deadlines, we spent like probably a whole week, from 10 a.m. to 10 p.m. and I didn't work on, and that happened for 2 or 3 deadlines. And eventually, this year we worked it out. But don't have to have an expectation either, because this is really hard. Like optimizing your networks is really hard. So we only have a very simple case that we can work out. So yeah, so I guess let me start with a little bit more kind of like a high-level overview of this area about optimizing neural networks. So I've been working on this like for a long time, and I think everyone know that this is non-convex, and that means it's NP hard in the worst case. So but in practice, SGD item works pretty well in practice. So the question is, why this works, and certainly I think what because the item and SGD works very well in practice, it means that the landscape is not going to be terrible, right? It's not going to be crazy like this. So so there are several ideas to kind of like analyze why in practice SGD can work. So one of the ideas is that all local minima are approximately global minimum. So and there are a lot of cases that people have been able to prove this is the case. So and most of these cases are linear algebra cases where you have some kind of matrix factorization, matrix completion, two linear rational networks where you don't have any activations, or you have a deep linear rational networks with some residual connections, so on and so forth. And the common technique is linear algebra, and it sounds like people use a lot of, like, at least in these papers I cited, the linear algebraic techniques are heavily used, and it's very hard to extend to nonlinearity. So the reason it seems to be that you don't have enough tools to reason about this set of local minimum, which is basically a set of solutions to the gradient is equal to 0 equation, and you add additional constraint that hashing is larger than 0. So I added this slide just for my own kind of like personal kind of like obsession in some sense, because I was thinking about this for a long time, and these are the two ideas that I always thought that there's still a chance, but I couldn't work it out. I know for me it's kind of like I already give up, but I want to kind of brought them up just so that maybe more people can think about it. So so one idea is that if all of these things are polynomials, then you can use algebraic geometry to study this thing, right? The solutions of some system of equations. That sounds like what algebraic geometry can do. But the problem seems to be that, first of all, algebraic geometry doesn't really give you an automatic solution understanding about like any polynomial system of equations. You do need to work out some details. And another thing is it's very hard to deal with this second constraint where the hashing is PSD. It sounds like you need some kind of like a positive or like a positive algebraic geometry, which I don't really know that much. So yeah, and another possibility is that I can think of is that you can use Castelli's formula. So where you count the number of solutions to some system of equations, and you leverage the fact that L is random, and then you can do some counting stuff. And I had a paper on this for some tensor decomposition problem, and it took like 40 pages to compute this Castelli's formula, and we only kind of like did a partial case, and it turns out that the issue is that it's very hard to calculate the expectation of this determinant of the hashing, which shows up in the Castelli's formula. At least I don't know how to do it. So yeah, so I guess but a little bit more kind of like taking a little bit higher level kind of perspective, it seems to me that now, like these days, I feel that maybe the fundamental challenge is not necessarily only on the technical level, but also on the level that actually maybe it's not true that all local minima are global. and it's probably far from, I never thought that this is exactly true, even from day one, but I always thought that it's kind of close enough to be true. But now I feel that maybe it's far away from true in some sense, so that probably it's not necessarily like the right statement to prove. At least you probably should allow the techniques to should allow some small number of bilocal minimum in some way. And you say that you never reach those bilocal minimum.
So I'm a little confused. Are you conjecturing that that these methods achieve a near global optima because the models work so well? And is it possible that there's another reason that they work well, and that even with, as you say, bad local minima?
Oh, I see. So yeah, so the question is that whether we even know that these methods reach a local or global minimum or approximate global minimum. I think that that's of course a conjecture, but it's not too crazy of a conjecture because the loss is very small. You know that the loss can never go below 0, and you see that empirically the loss go to at least for vision tasks where the loss is very small. So it's not that crazy to conjecture that you converge to an approximate global minimum. For language tasks, it becomes a little tricky because like the loss cannot be 0, right? There's a minimal entropy for the large language models, and I've seen that number goes down. Like we don't know what the entropy of the English is yet. So and that number becomes now 0.1, 1.1, 1.2, or even something like that. So I don't know whether it's a global minimum, but it still sounds reasonable to believe that you converge to a pretty good global minimum. Okay. Yeah. So basically, what I believe is that they are. So we are converging to a good. We are converging to a global minimum, but maybe they are still bad local minimum somewhere else that you never reach to. Okay. So and there's another idea which is kind of like a little bit related to this the last line where you allow some outliers, right? So in some sense, the other idea, the neurotangent kernel approach, is that you look at specific regions. You don't care about the global landscape. You say, I only care about the special region where I start close to my starting point. My starting point is some kind of like a random initialization with a particular scale. And then you identify a region which is often kind of like a ball. And you say in this region, the loss is actually convex or approximately convex. And there exists a global minimum in this region. And then you say, when you optimize in this region, you converge to that global minimum. And optimizing in this region is equivalent to doing a kernel method with neurotangent kernel, with the so-called neurotangent kernel, which I don't think we have to define for this talk. And this seems to be very powerful because you can apply this to various settings in deep learning, almost all settings, like even adversarial examples, large language model, or maybe deep reinforcement, and so on and so forth. But the problem is that it turns out that in reality, the SGD doesn't necessarily operate in this region. Because people are choosing different hyperparameters. So you have to choose the right hyperparameters for the initialization and the width and so forth to get into this region. But in reality, the practical algorithms don't operate in this region. And as a result, if you operate in this region, you don't have good test error. You don't have good training error, but you don't have very good test error. So and in reality, it's something like this, maybe somewhere else. So the third idea is the mean field analysis. So the idea is that you analyze the dynamics of the iterates as opposed to the landscape. So you forget about what's the global landscape, the loss function look like. You just care about how the iterates moves based on the dynamics. And also, more importantly, I think you approximate the dynamics of finite width networks by dynamics of infinite width networks. I have more details later, but that's the main point. So and the problem is that if you have even the dynamics of infinite width network is still highly non-trivial. You have some tools to analyze it, but it's still very non-trivial. And also the approximation error between the infinite width and finite width networks could grow up exponentially fast. So how do you really do this approximation becomes tricky. There are some of the existing results along this line that analyze the networks and give you end-to-end polynomial time results with modified SGD. So basically, what this means is that you first train the first layer with very small initialization to get good features, and then you train a second layer to get the coefficients on top of the features. And this is kind of like a two-stage algorithm where you, in the middle, you change the your algorithm. Even though you are in both two stages, you are using some SGD type of algorithms, but you are not optimizing the same set of variables. You are not using the same learning rate. It's abrupt changes. And there are many other works that kind of modify SGD in a similar way to get a two-stage algorithm, and then you can have this kind of like a feature learning step first, and then you learn the coefficients on top of the features. But in practice, what people these kind of algorithms don't really work, and you don't have to use this kind of like two-stage algorithm. You just do the same initialization. Maybe you have some learning rate warm-up schedule, but a relatively simple algorithm. Okay, so basically it was an open question to analyze the optimization of two-layer networks beyond quadratic and linear and quadratic activations with a sample complexity strictly better than NTK without modifying the SGD and GD and with polynomial width and polynomial time. So yeah, it's the end of all of this, not all. Yeah, so it's an open question to achieve all of this. And this paper basically gives you a analysis that satisfies the criteria above. We use quartic target functions and activations so that you cannot just only leverage linear algebra. And you have a better sample complexity than NTK, so you get the sample complexity guarantee. And you don't have to modify the gradient descent, and you also have polynomial width and polynomial number of iterations. So it's a fully polynomial time algorithm. Okay, so here is the setting. So so you have a with M neural network of this form. So you have a UI transpose X, that's the first layer. UI is the weight of the first layer, and you have M of these weight vectors, and you have a activation function called sigma, and then you add up all of the neurons, sigma UI transpose X, and you average by 1 over, you divide by 1 over M. So basically this means that the second layer are being all 1 over M. So you are just you don't choose the second layer. It's just really just the second layer is just all the weights are 1 over M and not trimmed. And here we have some kind of like a normalization. So UI and X are both unit norm. That's for some mathematical convenience. And we are using this kind of Meanfield approach, at least on the conceptual level. So the Meanfield approach, the main idea is that you rewrite this neural network in this form. You view it as an infinite weight networks in some sense. So basically, if you have an infinite weight networks, what you do is you say you have a family of U's, and this U's forms a distribution, and then you write the sum as expectation over the distribution of U's. So in some sense, you can view the finite weight network as infinite weight network by saying that my distribution rho is really just a discrete distribution supported on U1 up to UM. And this is a uniform distribution supported on U1 up to UM. So basically, if you choose rho to be this, and then these two equations are the same. And the width, on the other hand, is the size of the support of rho. So this is a way to kind of like So basically now you have a way to describe both infinite weight network and finite weight network. If the weight is finite, then that means rho is a discrete distribution. If rho is a continuous distribution, for example, if rho is just Gaussian, then you have infinite weight network. You have basically you are sampling from Gaussian distribution for the weights. So this is a little bit nicer language to some extent, so that you can unify these two cases. And we have quartic polynomial activations, sigma with a non-trivial degree 4 term. For example, the kind of the design choice we have is that we want sigma to be able to, we want sigma can be equal to the degree 4 approximation of ReLU under some basis. So I'm not going to talk about details here, but basically you can allow a quite kind of like a number of possible degree 4 polynomials, including the degree 4 approximation of the ReLU. Okay, so and a target function is the so-called single index model. So basically, you have a single direction Q, and you project your data into the direction Q, and then you have an unknown function h on top of it. So h is the unknown quartic polynomial that can be non-monotone, and Q is the unknown direction. And this is a very common test bed these days for studying two-layer networks. And one of the reasons is that, of course, it's nonlinear. That's good. And also, one of the reasons is that for this kind of target functions, you can see this so-called kernel and the statistical limit gap, in the sense that you know that there's a lower bound or impossibility results for using kernel approach. So if you use NTK or use any kernel approach that is generic, then it requires d to the 4 samples to learn this model. And the 4 means it comes from the quartic polynomial. And statistically, I think very likely you should just only need d samples, because you only have d 3 parameters. That's the dimension of q. And in the more extreme case, if q is known, if you really know q, then actually you just need probably a constant number of samples, because what you do is you say, I'm going to create a new feature map, which just maps my x to q transpose x squared, q transpose x cubed, so that I have the right set of features. This is very informative features, and then you just have to learn the h, which just requires probably 5 parameters. So you need only O of 1 samples to learn this once you have got the right features. So basically, this is saying that if you don't have the right features, you just use a generic feature, for example, NTK or any other generic features in a product feature, for example, and then you need d to the 4 samples. But in the extreme case, if you know the q, then you have O of 1 samples. And what should be the case is something in the middle, where you don't know the q and you learn the q, and after you learn the q, you get the right features, and then you spend probably O of 1 samples to solve the problem. And in some sense, this is also give you the next kind of conceptual understanding that neural networks can go beyond just the generic kernel, because neural networks allows you to learn a good kernel, so that you have better sample complexity. Yeah, so that's why we work with this. And just a very quick kind of like background on the precarious settings here. So if you, in the most trivial case, suppose sigma and h are the same, then you have expressivity, and you can see trivially you have expressivity, because you just have to choose rho to be a point mass and u to be equal to q, and then these two functions are the same. So that's the most trivial case. But this is not a case we're going to work on. We're going to work on the cases where sigma can be different from h, and in those cases, the expressivity is a little bit non-trivial, and what happens here is that because the target function only has one direction, which is special, which is q, so the optimal way to fit the target function with this two-layer network is to choose your u to be symmetric around q. So you shouldn't do anything special in any other directions. The only thing you do is that you choose some distribution of u that is symmetric around q. And you know that if you choose u to be like that, then you average out over u here, then you are going to have a function that is only a function of q transpose x, and the distribution of the I'm not sure. The distribution of q transpose u. Basically, the only thing that matters is the projection of everything to the direction of q. Right. So that's the optimal way to fit this kind of like model. So the optimal solution should be a symmetric function. The optimal neural networks should be a symmetric distribution around direction q. And you can actually do this, in a very precise way. You can give the almost kind of like a sufficient and necessary conditions on when such a expressivity can happen. The conditions are a little bit kind of like tricky to state, so that's why I omitted it. But you can characterize that almost exactly, and our results applies to basically all the cases where you have expressivity, except a small subset of corner cases. Okay, and under this setting, what we can prove is that so if you use a gradient flow on the actually projected gradient flow, because you have unit norm constraints, you do projection on a unit norm. And if you use loss function, which is just the standard empirical mean square loss, and you use polynomial weights networks, and you use d to the 3.1 samples, then you can achieve a little of 1 population loss. And at the same setting, if you use a kernel method with any inner product kernel, it requires d to the 4 samples to achieve the same error. Yeah, so the rest of the time will be about how do we prove this. And the plan to prove this is that you go through this kind of like Meanfield analysis. So you first analyze the training dynamics for infinite width, infinite sample case, and then you compare the dynamics of the infinite width. You compare the dynamics of the finite width and finite sample case with the dynamics of infinite width, infinite width and infinite sample case. So this is a kind of like some kind of approximation kind of like perturbation, kind of like theory kind of stuff, and this is about the population case.
Can I ask
Yeah.
if sorry, thank you. If sigma and h are say equal and ReLU, I know you're not exactly doing ReLU, but like is this a convex objective or no? Like the loss ultimately as a function of the weights.
If sigma and h are both, I don't think so. I think if you only have one u, it will be. I think that's so. Suppose your system you only allow one with one, so then it's gonna be not convex but quasi-convex, and also that requires you to know. Okay, so because you already know, so because you in that case you know the h, right? So sigma is equal to h, so you know the h, and basically if you know the h, and if h is monotone, and you only have one weight vector, then I think KKKS like 2011. So there's a paper that shows that that's a quasi-convex situation, which means quasi-convex means that the gradient is always larger than the loss function. And then you can prove the convergence. Yeah, but once you have like multiple u's, it becomes tricky because it cannot be actually once you have so this is an interesting thing. So once you have a system with permutation invariance, then there's no way it's convex anymore, because you can always permute two different u's. It's like you swap two u's, and it's the same system. Right, so under those cases, I think you can actually, Runge has a blog post that proves that under these cases, you must have stationary points. And it's a pretty generic proof, like you don't even need to, doesn't have to be a neural network.
Can I ask?
Yeah.
Can you explain a little bit this order one population error? Like, why this is a good thing, and how does this compare with like your initial error?
Oh, the initial error, yeah. So the initial error is on the order of 1. So it's really just the absolute constant. It's like at least in the I omit some of the details here, but in the under the setting that we can prove formally, the initial error is on the order of 1, maybe a constant and a half, and that's why achieving something less than 1 means you learn something.
Okay, I see.
So the optimization problem class, is that still an NP hard problem class in terms of complexity? And does your theory say anything about, so you're saying something about the sample complexity. Is the computational complexity still potentially exponentially large?
Oh, the runtime is still like is polynomial because you have polynomial number of iterations, polynomial number, everything is polynomial. So the runtime is polynomial. But I don't think you can talk about NP hardness here because you have only one target. Basically, you only have one loss function, right? So when you have NP, to talk about NP hardness, you have to have a family of problems. So right now you only have, you still have a family of problems to some extent. But
the H function can vary, right? The H function.
The H function can vary and the Q can vary.
Right.
Yeah. So then this is not NP hard under this kind of family for this family of functions. Yeah. So I'm going to start with the one-dimensional case and the infinite width, infinite sample case, and then I'm going to talk about the approximation. So let me just remind you the notation I'm going to use. So I'm going to use the right-hand side as my notation for neural networks. And once you have this notation, the population loss in the left-hand side is going to be y minus the neural network square. And on the right-hand side, we're going to just write y minus f rho x square, and the rho is this basically captures the distribution of u. And you can compute a gradient for both of these cases. The exact details don't really matter. But you can compute a gradient with respect to each of the particles on u, and you can get how does u moves over time. So basically, the way that I think about this is that u is kind of like a particle, and rho is the distribution of the particle. And rho is merely just a way to name the particle. You don't really actually in this whole talk we are not going to compute the density of rho. So rho is just there just to say this is a collection of particles. Okay, so basically each of the particle u moves according to this rule, And this rule depends on two things. One thing is depends on where you are at, right? So which vector, which particle you are talking about, and the other thing is it depends on the rho, the distribution of the particles. So that's the how does this work. So at any time, this is a vector field because the rho is fixed, and then you just at every point you have a vector field. And what happens is kind of like this is still setting up the language in some sense. The way we think about this is the following. So at the beginning, you have a bunch of like particles, right, which forms probably uniform distribution over the sphere. That's because that's how you initialize. And then it turns out that the way to think about this is probably the best way to think about it is that you think of like every neuron, every point have a there's a starting point, right? So you say chi is the starting point, which is the neuron in the initial situation, and then you can track how does this point moves, right? So you can say ut chi is the is where this point moves toward at time t. So and you call that ut chi, and it's the location of chi at time t, and you can write this dynamics, and then you can say because you have so many points that are all moving together, and at every time you can define rho t to be the distribution of all the points, the locations of those points at those times. So this is the picture. I guess the notation is a little bit complicated, but basically this is what we're talking about. Okay, so basically you are tracking all of how all of these points are moving, but note that how does each point move depends on the collection of all the other points, because the dynamics depends on rho, the distribution at that time. But how does each point move don't depend on individual other point. It depends only on the collection, the collective behavior of all the other points. So and the key observation here is that once you have this population case and we have infinite sample case, then because everything is very symmetric, so because y is a symmetric distribution around Q, so y is a function that is kind of like symmetric around Q, and your initial distribution is symmetric around Q because initial distribution is just uniform over the sphere. So actually, you can show by induction that the distribution of the points is always symmetric around Q. So basically, the whole dynamics is always kind of like about those symmetric distributions around Q. So basically, suppose this is the direction of Q, you can see the points basically moves in pretty kind of like ordered way. So like it's always symmetric around Q, and the only thing that matters is the movement in the direction Q. And then actually you can do this mathematically by proving that suppose rho is symmetric around Q, and you project the neurons or the particles to the direction of Q, and you call that W, then the loss function is actually of the form of this form, which only depends on the distribution of W. So the only thing that matters is the distribution of the projection of the particles in the direction of Q. And actually, this formula is very similar to, it's just a moment matching thing, right? So we are basically matching the second moment of W to some scalar gamma 2 and the fourth moment of W to some scalar gamma 4. And that makes it's much easier to analyze. Of course, it's still a little bit tricky because they are still, this is still not convex and so on and so forth. But right now, it's a one-dimensional dynamics because you only care about the one-dimensional distribution on W.
So is this via Taylor expansion or is this exact?
This is this is exact. I think the only this can be exact, but the approximation is not from the Taylor expansion. It's from something like just I didn't write it precisely. So I think the exact formula would be something like there's a second term here inside this as well, which is not very important. But otherwise, it's and this is using spherical harmonics. Right,
so, but I assuming some specific sigma. Did I miss that?
So the C0, C1, C2 depends on sigma.
No, yeah. Oh, I see.
Yeah. Sorry, does that answer the question?
Okay, yeah. Thanks.
So this is basically like a spherical harmonics or Boolean function. It's kind of like a little bit like the spherical case of the Boolean function analysis. I'm not sure whether this can explain that very well. So basically, the way to think about this is that you expand this, you expand the square, and then you expand everything in the spherical harmonics kind of like space. This is my cheat sheet. I'm not sure whether it's really useful. So So the way I think about spherical harmonics is that you start with the one-dimensional case. You have this Legendre polynomial, which forms a one-dimensional orthonormal basis. And once you have this one-dimensional orthonormal basis, then you can express expand every function that is only a projection to certain direction into this form. So this is a function of x, but it's only the only thing matters is in the direction of u, and then you can expand it because you treat it as a one-dimensional function. You can do the one-dimensional Legendre expansion, and as a result, and also there's one important thing about the Legendre polynomial, which is actually this is something similar to this. It's also true for Boolean case as well. So what's important is that if you have two, you take the inner product of two functions like this. So both of these two functions are those kind of basic forms where you project to one direction and you apply a Legendre polynomial. So and you average out x, then the only thing that matters is the inner product between u and v. And also these two j and k has to match, otherwise it's 0. So in some sense, this is saying that this is this kind of objects are functions in orthonormal functions in the high-dimensional space.
Sorry, it just means something. Does the distribution of x matter? So what happens if they are on a cube or something? So does it matter to be on a sphere, the distribution of x?
So to use all of these tools in a precise way, yes, it does matter. So it has to be uniform over the sphere. The distribution of x has to be uniform over the sphere.
I see. And can you go back to the previous slide? So
Yep.
what is this showing? That the movement toward like the direction of q? So is this as we are training, or what is it? What the animation shows? I don't understand.
So the animation here shows that I think the animation is more relevant to here. So this animation shows that all the points only move. The only thing that matters is the direction q, and the distribution of the point clouds is always spherical, or it's always symmetric around the direction q. So that's kind of like a property you can maintain by inductive hypothesis, by induction. Yeah.
So is it throughout the training, you mean, right?
Throughout the training, if you have infinite width and infinite sample.
Thanks. Thank you.
And that's why you can reduce this to one-dimensional case. Yeah. So anyway, so I think I'm gonna. So and then you use some of these formulas. I guess if you do something in the head, so if you expand this, you're gonna see a lot of things like this, and then you get rid of the x, and you only get u and v, and then you can rearrange and you get some formula like that. Yeah. Okay. So and then you can deal with the one-dimensional case. And for the one-dimensional case, you can compute the gradient with respect to each of the particle, which is a degree 3 polynomial. And here I'm visualizing how the particles are moving. I guess let's see whether it's working. I couldn't get a very nice visualization because I'm like the points don't move that much, so that's why. Is it moving? Yes, moving. It takes like 2 minutes to see. Anyway, let's continue. So so basically the points are moving gradually according to these dynamics, right? And the kind of the first thing we studied when we studied this dynamics is that when is the stationary scenarios, right? So what happens when it gets stuck? So and what does it mean by getting stuck? It means that all the particles don't move, right? As long as one so actually this is the beauty of this kind of analyzing this kind of dynamics, which is a gradient field of some objective function. So once your dynamics is the gradient field of objective function, you know that the only thing that it can get stuck is that all the particles don't move. There's no way you can have cycles, because as long as some particle is moving, then your loss function is decreasing, because you have the descent lemma for gradient descent. So how much you reduce the loss function depends on how much the particle moves, and there's an equality. So that's why the only way that you can get stuck is that all the particles don't move, and that's the stationary scenario. So and basically what happens is that eventually what you do is at the end of only the last bullet is what we wrote in the paper, but the thought process is that you first analyze all the possible stationary points and see when you can get stuck, and then the bad thing is that you can indeed get stuck. This is a non-convex loss function, so you can get stuck at the stationary point in theory. But what happens is that you will never get close to the stationary point. The stationary point, some of them are not stable, and some of them are just never get close to them. So we have a lot of case study, maybe like a totally of 6 cases, and you basically for each of the cases you design some potential functions to say that you never get close to the stationary point. And if you're far away from the stationary points, you can prove this kind of like Polyarc conditions where you show that the gradient is always relatively big compared to the loss function. So unless your loss is small, you always have good gradient, and that means you can decrease your loss function. So and that part is relatively standard. After this, as long as you show this, and then the rest of the part is standard. So the hard part is how do you show you never get close to a stationary point, and how do you even characterize that? How do you characterize the closeness to stationary point? And there's no one thing fits all kind of like characterization. For different cases, we have to set a different characterization, and there are different ways to prove this for different cases. Okay, so the things that I'm hiding here is could be a little bit messy. Yeah. Okay, so that's what we did with the one-dimensional case, and now let's talk about the finite width and finite sample case. So how do you compare the finite width and finite sample case with the infinite width, infinite sample case? So here's the picture for the infinite width and population case again. So you have a lot of points and they are moving in some way. And how do you compare this with the, okay, so let's gradually move to finite width and population loss, right? So let's first finite width and the finite samples. But let's first start with finite width and population loss. So you still have infinite number of samples, but you only have a finite number of neurons. And that means that you start with a discrete distribution, maybe just M neurons. These blue points are M neurons. And each of these neurons are moving according to the same, a similar rule as before, but not exactly the same, because how does each neuron move depends on the distribution of the neurons, and the distribution of the neurons changes. So each neuron, the rule for each neuron is also a little bit different. But at the end of the day, each neuron moves, and then you can define rho tilde t to be the distribution of this new set of neurons at time t, and the dynamics depends on both the particle and the distribution of the particles. Okay, so that's what happens with finite width. And once you have infinite finite width and empirical loss, the only thing that's different is that the loss function is a little bit different. So your gradient is a little bit different. So you have a little kind of like approximation. Before it was like L of rho tilde t, and now it's L hat of rho hat t. Rho hat t is the distribution of this new system of particles at time t. So basically, let me just put it down. So basically, we want to move from here to here, and you can see there are a few type of differences. And the way that we bridge these differences is that you start from, again, the population case, and you first do consider intermediate dynamics. So this intermediate dynamics is almost the same as the population infinite width population loss dynamics, except that you start with this discrete set of neurons. But note here that I start with a discrete set of neurons, maybe only just 5 neurons, but my dynamics is exactly the same as the dynamics here. I'm not changing the dynamics at all. I'm only changing the initialization. So that means that so this picture and the picture before, the only difference is that the new set of this one is just a subsampling of the previous one, because I didn't change the dynamics. The dynamics is still computed based on the population, the infinite width neurons, right? So that's why this is a very simple case, because it's just a subsampling, and you know that basically the rho bar t, this distribution is almost the same as the previous distribution, because it's just a subsampling. Even though this rho bar t is very, in the Wasserstein distance, is very far away from the rho t, or in TV distance, rho bar t and rho t are very different. But still, if you look at any of the functional form, like you look at integral probability metric, right? So any of the functional form, as long as the function is kind of like has restricted complexity, then the rho bar t is kind of very close to rho t. Okay, so this part is easy. And then the second part is just that, okay, now you look at the finite width empirical loss dynamics versus the intermediate one. The only difference is that you couple the initialization. You say they have the same initialization. And then the only difference is the dynamics are different, right? And dynamics are different in several ways. One way is that the loss function is different. Another way is that the distribution is different. And also, once you kind of like like in the first step there, you have the same initialization, right? And the second step, you already kind of like the points are already different, right? They are not at the same location anymore. So you start to diverge, right? So your starting point is even different. So basically, the gradient here and gradient here are computed at different particles. So that contributes to another source of differences. So but you basically have a slightly you have several differences in terms of how the neurons are moving, but they start from the same set of blue points. Okay, so and then how do we deal with this? This is pretty much just a pretty brute force kind of like coupling. So you just couple based on initialization. You just want to say that the U hat, the real dynamics is very similar to this UT, the ideal dynamics, pointwise, right? For every possible initialization, or maybe in average over initialization. So basically, you're just bounding the UT chi minus UT in T. And as I kind of like alluded before, so there are several differences, right? So you can expand these differences, the differences in the dynamics into 3 terms, and each term has only one diff, right? So here, this is the differences in terms of the point you are at. This is differences in terms of the distributions of the other neurons, and this is the differences in terms of the loss. And for the loss functions, this is about sample complexity. And for the other two, it's really about how the dynamics diverge, right? Because eventually, eventually these two dynamics will diverge from each other at some point, just because the errors becomes bigger and bigger. Right. So and the temptation is that you want to get a bound of the form that the error blows up in some kind of like way. So you say the error is probably smaller than this is dt, so blow ups in some way. It turns out that this kind of the first order term and third order term are kind of not that very important. The main important term is the second order term, which contributes to exponential blow up. So basically, even your bounds only have this term, beta times u hat t minus ut squared, then you're going to have a exponential blow up in terms of the error. And that error is, and the exponential, the blow up rate is kind of something about beta. And so that's why the beta will be very important here. So, okay, so that's the challenge. So basically, once you have exponential blow up, it's very subtle, because if you have the wrong beta, basically suppose your estimate for beta is wrong by a factor of 2, even by a constant factor, then suddenly you grow too fast in some sense. So that's the hardest part. So so basically, and also the exponential divergence is also unavoidable in this case, which makes it even subtle, right? Because you cannot really get a better rate. And the reason why it's unavoidable is that if you look at only the second order term, so basically if you only look at this term, like where you match the second moment, and you can see that the dynamics for W is going to be something like the gamma 2 minus the error in the second moment times W. So this is kind of like power method, especially when W is small. Suppose all the W's are very small, then this is just gamma 2 times W. So basically at the very, very beginning, when all the W's are very small, then you are basically having a power method. And the divergence of two, if you start from different starting point, then you are going to have basically have a multiplication gamma 2 in front of the error. So basically, if you start from different points, then the error just keep blowing up because it's power method. So so basically, what happens is at the beginning, when W is small, then you are having power method. You have really exponential divergence, but eventually, the next thing is that eventually you're going to converge. This moment will match gamma 2. That's how you get a loss small, and then at that point, the divergence speed will slow down. So that's kind of the savior. So you have to leverage this fact, because otherwise you just keep diverging and there's no way to control the error of these two dynamics. So this part is we can do, but how do you deal with this part? Right? How do you control the exponential divergence in the beginning? And the way that we fix this is that we say let's do a little bit more careful analysis, right? I mentioned that the constant factor matters, and this is how you kind of get the right constant factor. So you cannot just really get exactly the right constant factor. Suppose you just use a single scalar here, call it beta, then that beta cannot be the right constant. So you make that constant kind of more dependent on where you're at. So basically what we do is we say this is the you shade the error kind of like between the two dynamics grows in this way, but also the W itself also grows in this way. So the W becomes bigger and bigger, right? As you can see from this power method dynamics. So and it happens that these two factor here, these two scalar here are exactly the same scalar, and you work very hard to make this approximation actually even almost equality. So I think the exact constant would be that this is a 2 here and this is a 4 here, something like that. So and then there's some lower order terms which you can ignore, and then you can compare the two exponential. So both of these two kind of like recursion kind of blows up, exponentially fast, but they blows up exactly at the same rate. You know exactly the constant in front of them. So I see comparatively, but you don't know exactly what this quantity is, but you know this one, kind of like blows up, by exactly a factor of 2 faster than this one, in some sense. So and this dynamics, can never blows up like forever, because the W has an upper bound. Like you cannot just W cannot go to infinity, right? So W is kind of like between -1 and 1, and then that's how you control how long this one will blow up, and then you use that bound to inform the other bound to show how the other bound kind of blows up. Yeah, so that's the technical part of this. But I think so I can imagine there are many other cleaner analysis for this eventually if we work harder on this. But the point here is that I think the real kind of like a clicking moment for us is that we realize that the exponential divergence is not avoidable, and it's not avoidable only because initially you have a power method, and that's the only reason why it's not avoidable. And after that, I think it's usually just a matter of time to figure out what's the right analysis to leverage this fact. I think I'm a little bit early. Okay, that's good. Okay, so yeah, just a quick summary. So we have this Meanfield analysis for coordinate target functions with unmodified SGD with polynomial weights and iterations. And the technical innovation is that first you leverage symmetry and spherical harmonics to reduce the population dynamics to 1D problem. And then you analyze the population dynamics with details. This is not very easy. I didn't talk too much about it, but this is a little bit messy. And then you have a tighter bounds to couple the error between the population dynamics and the finite weights, finite sample dynamics. And the key innovation there is that you have a tighter bound by comparing the signal with the growth of W with the growth of the W. That's what I call signal with the growth of the error. And I think there are probably a list of open questions, to see how does this technique extend to more complex settings. So one of the possibilities you can generate is to ReLU, and at least for the one-dimensional case, the spherical harmonics still works for ReLU. It's just they have like a longer expansion, but the dynamics will be complicated when you have like a higher degree terms. The sample complexity, we don't really believe that d to the 3.1 is the best one. But that probably is because we didn't do a concentration inequality in the best way. It already takes like 15 pages to do the concentration inequalities with all the atoms are kind of like with some of these concentration papers. So that's why we didn't work harder on that. And you can also have the multi-index model, and you can also try to deal with optimizing both of the first layer and second layer. Yeah, I guess that's all I want to say. Thanks.
Any more questions for Tengyu?
So in the proof outline, you went from, so you did a finite number of neurons and finite samples, but you haven't yet gotten to finite optimization steps. So it's still a continuous time gradient flow. In the paper, do you do gradient descent? And if so, were there any technical difficulties in going from continuous to discrete time?
Yeah, so in the paper we do have an analysis for discrete time, where you use like a inverse polynomial small learning rate. There's no any additional challenge there because this is actually what we added after we have the first version. This is the second version. So the reason that is not a problem is because typically the challenge to discretize is that your error can like the again, it's another approximation, right? The discrete time algorithm versus the continuous time algorithm, and these two dynamics might kind of like diverge, right? And you just reuse the same kind of like analysis to show they don't diverge as fast as you they don't diverge very fast. Yeah, so it's the same analysis pretty much.
I see. So, but so in addition, you would also need that in the continuous time, it wouldn't take exponentially long in continuous time to get to the like a desired solution. So is the not fast convergence in time, is that achieved with the like the PL condition that you referenced?
Yeah. So that's a great question. So for this for the initial phase, because you compare with the growth of the signal, you don't really care about how long it takes, because even if it takes a long time, because this quantity never blows up, so by comparison, like your error that doesn't grow up, doesn't kind of like blow up that much. But in some of the later stage, we did have to have absolute bound on how much the error grows at every iteration or for every unit of time. So and for those cases, you do need an absolute bound on how long you run the algorithm. So that's why here I didn't. I was kind of like I sweep this end of the rug, so I only say a little of one. So because the analysis can only work until it reach a little of one error, it doesn't work for every epsilon. So if epsilon is like 1 over d to the square, then the analysis doesn't work anymore. So that could be an open question as well, like how do you analyze that final like if you run it for long enough. I think if you run it for long enough, this should still like everything should still work. Fundamentally, it's just like you need a little bit different analysis to show how to kind of like to a more kind of careful analysis to bound how does the error grows eventually.
Yeah, one last question. So the 3.1 is not a very round number. Is there like a simple explanation as to why you have 3.1 as the exponent?
Yeah, I think it's d to the 3 times anything that is super polylog, maybe super. So basically, it's the d to the 3 plus anything, any constant, but it cannot be d to the polylog. I think. Sorry, it cannot be d to the 3 times the polylog b. That's not big enough. Yeah, something like that. Yeah.
Thank you.
I guess, do you mind sketching some intuition where the d cubed bottleneck comes from? Like if it's degree t polynomials, should I just think it is like t minus 1 plus middle of 1?
I think there is I don't know, like the sample complex analysis is very complicated because what happens is that you need to bound, let's see. So basically you need to bound the differences between L hat and L. Right, so that's how the sample complexity is done, and also actually I need to bound nabla L hat versus nabla L. And what is nabla L hat and nabla L? So that's where I think I had this somewhere very briefly. Whoops. Yep. So this is the L, right? And L hat will be you use the empirical samples instead of the expectation. And because this L is so this is nabla L, right? Because nabla L is a kind of like a complicated object. So you have a degree 3. The sigma prime is degree 3, and you have another x, so it's a degree 4 polynomial, and you have this, which is degree 4. So basically, you are bounding a degree 8. So basically, you are doing the concentration of a degree 8 polynomial. And you have to do uniform convergence. Actually, there's a lot of subtlety there. Like you cannot do uniform convergence over the entire space. You have to do uniform convergence over a tube around the trajectories you might possibly like. So basically, there's a trajectory for the population dynamics, and you build a tube around that trajectory and say you never leave that. You dynamic control that you never leave that tube, and for that tube you do uniform convergence. So basically, you have a uniform convergence for 8 degree polynomial over a kind of like a tube. So and that requires so we are using some of these papers by Adam Zak et al. That bounds this things like bound the concentration of U transpose x to the power p. right? And you reuse that many times, and I think in that we know some part of those analysis is very tight, but some other parts is not tight. So that's why we don't know where we lose.
Any other questions? All right, so let's thank you again.
Thanks.
And now we have a break until 3 p.m.